So let's look at three numbers: 104 million, 1.7 million, and 29,000. These are representative ChatGPT interactions per hour, per minute, and per second of the day, amounting to 2.5 billion interactions per day. And these are as per OpenAI numbers. So given this large number of interactions that are taking place every day, what is the amount of energy that is being consumed? So to do that, we have to look under the hood, and under the hood we have transformers. And we know how transformers operate. The important thing is the underlying workhorse are horses, are matrix multiplications. And if we look at a representative example, so typically a large language model would have about 70 billion parameters, and this would amount to about 500 to 2000 major matrix multiplications per generated token. Right? Now, if we consider that each of the 70 billion parameters take part in a MAC operation, a multiply and accumulate operation at least once, so that corresponds to about 70 billion MAC operations per token. And a typical short response is about 100 tokens. So we are looking at about 7 into 10 to the power 12 max per response. Putting this number together with the 2.5 billion interactions, that comes to about 1.75 into 10 to the power 22 max per day. Okay. These are multiply and accumulate operations which are happening per day. And to get a sense of this magnitude, there are 10 to the power 22 stars in the observable universe. Right? So that's the kind of numbers we are talking about. So since we know what are the total number of Macs per day, can we calculate what is the total amount of energy per Mac operation and then just simply multiply it? Okay. So firstly, what is a multiply and accumulate operation? So if we have a matrix, then we know conventionally we would do something like this on a pen and paper. Alternatively, we can also do it recursively, where we initialize P with a value of 0 and then multiply and accumulate and go down the column or go across the row. And this is essentially the multiply and accumulate operation. Now, the typical energy consumed per float operation is of the order of 0.1 picojoules, that's 100 attojoules. So these are really efficient operations. If you're working with ints, they would even be better. So that's about 10 attojoules. If you are fetching data from memory, which we have to, so that corresponds to about 5 picojoules-ish, right? So the numbers can vary. So it's just an order of magnitude. So the total energy taken per multiply and accumulate and also the memory read and write can be calculated. So we have energy for one multiply and one accumulate. So that comes to 0.2 picojoules. Energy for two reads and one store, because we are reading two numbers, we are doing the operation and then we are storing it back. So that comes to about 15 picojoules. So the total energy is 15.2 picojoules. Now the number might seem very small, but the important thing is 98% of this energy that you see is just needed to move data. That's an overwhelming fraction of the energy spent to do the MAC operation. Okay. So now that we have an idea of the energy per MAC operation, we can put it together with the number of Macs per day, and that comes to about 74 megawatt hours per day. So this is a number at this point. So let's put some sense into it again. So 74 megawatt hours per day can power 14,000 homes per day or 40 homes for a full year. It can charge one electric car to travel 550,000 kilometers or go around the earth 15 times. And it is roughly 1/10 of the energy consumed by a modern AI data center in a day. So that also gives you an idea of how much energy is being consumed by data centers, right? So this is two numbers that I would like you to keep in mind. So one is the 74 megawatt hours per day, and the other one that 98% of this energy that you see is just moving data. You're spending it just for moving data and nothing else, right? So that's very interesting. Okay. Let's ask another question. What are the compute timescales? Okay. And if we want to answer this question, then we have to understand how a GPU performs a matrix multiplication. So typically, if you want to do a matrix multiplication, say a 4 cross 4, you can always do it by pen or paper. What a GPU does is it multiplies much larger matrices. So it takes a strategy of tiling the elements together. And once it tiles these elements together, then it can do a batch process and process these tiles independent of each other in a parallel fashion. And that's what GPU is really good at. So for instance, C11 is an individual process, C21 is an individual process, and so on and so forth. And later you can combine these results together. The interesting thing is you do have redundancies here, and that is what GPUs use to increase the arithmetic intensity of operations. Right? That is, you reuse as much memory as possible without bringing it back from the main memory. Right? So how does this actually look like in a GPU? So if you take a toy example, you would have a high bandwidth memory where you load the matrices that you want to multiply. You pass it on to a cache memory where you store the tiles, and there is an exchange between another cache memory and this cache memory of the tiles. And this L1 cache memory now communicates with the tensor cores and does the fast multiplications. And once the multiplications and the accumulate operations are over, it pushes the result to the high bandwidth memory, and then later it comes back to you on your screen, okay, in as many words. Of course, this is a toy model. Do take it with a pinch of salt. But this is good enough to get an essence of timescales. So say you're working on a 70 billion parameter instance of an element, right? So the data transfer from a high bandwidth memory is of the order of 3.35 terabits per second. And this is roughly, or this is actually the NVIDIA numbers, H100 SXM numbers, right? So if you want to transfer 70 billion weights at one shot, if we can do that, right? That would take about 41.8 milliseconds. So you load the whole matrix onto the memory. Now compare that to tensor compute. The tensor has a throughput of 989 teraflops, and that corresponds to about 4.95 into 10 to the power 14 MAC operations per second, right? The total time taken for a token to be processed, so we know that we have a 70 billion number, so we divide that with the MAC operations and we get about 142 microseconds. So you can already see there is orders of magnitude difference between the time taken by the memory to transfer data, or time taken to transfer data into memory, and the time taken to compute. And this is roughly of the order of 300. And this is well known in the community. This is the famous memory wall, or the von Neumann bottleneck that we all talk about. Essentially, L1 caches don't store tiles indefinitely, and the tensors are operating on data much faster than the memory can supply it. So that leads to a latency bottleneck, and that's the memory wall, right? Now GPUs know this, GPU manufacturers know this, they optimize for that heavily, but you still have this wall, and it has implications for low batch LLM implementations, edge inferencing, etc. Right? So let's put this together with the earlier number that we had. 98% of the energy is just needed to move data. And there is also a latency aspect, that the time taken to move data into the memory is almost 300 times more than the time taken to compute. Okay, again, ballpark figures, order of magnitude numbers, but it tells you that we have an efficiency problem. We have an energy efficiency problem, and we have a time efficiency problem, right? And this is what scientists are working to solve. This is what industry is working towards to solve. And this is where neuromorphic computing enters the picture. So neuromorphic computing is brain-inspired computing architectures, and it asks a very simple question, in as many words again. Can we make computing more efficient by emulating brain-like processing and or co-locating memory and computing? These are seemingly simple questions, but they have spanned a whole ecosystem of research. I wouldn't even call it an area, I would call it an ecosystem of research, because you've got different technologies contributing to this area, and each technology is very rich and diverse in its own way, right? So for example, if I just take photonic computing, it has got several paradigms within it. So you have linear optical computing, you can use diffraction to do computing, you can work with metasurfaces. Scattering media nowadays is very interesting because you can perform matrix multiplications at scale. Photonic reservoir computing is a very interesting and a very promising example of neuromorphic computing, and so on, right? And this is not limited to labs. a high TRL level research has already been done in these areas. SpiNNaker is one such very good example with research going back to 2013. Now they have SpiNNaker 2. 𝗵𝗿𝗍𝗄 is another well-known example, also showcased on YouTube and Veritasium. You can have a look. And you do have IBM, the big player who is doing neuromorphic computing and recently published some work in Science, right? This is a very active field and it's very actively evolving. To give you an example or a flavor of that, let's look at two architectures. So this is the first optical neural network, which was developed in 2017. And this is the fairly recent universal photonic artificial intelligence accelerator, or a photonic GPU, developed in 2025. Okay. There is a span of 8 years between them, but within these 8 years, a lot has happened. So if we consider the optical neural network, so it was actually the first optical neural network that tried to solve that initial problem, storing the weights where the compute is happening, and also reducing the amount of energy that is being taken when the compute is happening. So it was the first optical neural network using weights stored within the silicon photonic integrated circuit. And there was also light speed matrix operations happening with passive energy consumption, essentially meaning that you just let light pass through and it does the computation for you. The problem with this was scale, and there was also issues of drift and noise. And this was in 2017. Now, if we cut to 2025, right? This was a demonstration of the first true universal photonic accelerator, in the sense that you decide what the architecture it is that you want to run on it and you implement it. Okay. In the earlier case, the architecture was frozen in, the problem was frozen in. You could of course make some changes here and there, but essentially the problem was frozen in. In this case, in the 2025 case, you decide what you want to run on it. Okay. And ResNet, BERT and DeepRL are fairly real world workloads. The game changer was exploiting the best aspects of photonics and electronics. Photonics is really good at fan out, right? It spends really little amount of energy. You can divert the energy to different places that you want it to go. And electronics is really good at processing and maintaining precision. So this is why, and this is how this particular processor was able to deliver numerical precision compatible with conventional AI workloads. And this is considered to be a watershed movement for photonic processors, right? And the industry was watching, it took action, and immediately we have NVIDIA jumping into the picture. NVIDIA employed photonic fan-out at scale. So this is the NVIDIA Vera Rubin with Spectrum X Ethernet with co-packaged silicon photonics. So you basically put the photonics right onto the chip. And you need this because if you are thinking about million GPU AI cluster workloads, which is where everybody is moving towards these days, you need efficient data transfer between GPUs on a scale of a data center. And if you do it with electrical wires, you lose a lot of energy. There's a lot of distortion. You know what happens, right? When you use wires. And we don't have that problems when we use optics or optical fibers, right? We do have other problems, and that's a story for another day. But the main problem of distortion, the main problem of the usage of excess energy, all of that is kind of resolved with optical fibers and optical interconnects or photonic interconnects. And here we also see a classic push-pull between research and industry. Research wants to answer the big question: how can I make computing both energy efficient and time efficient? And industry is pushing scale, right? And this is a wonderful example of how academia and industry work together and also compete with each other. Another classic example, Light Matter, which actually developed the photonic accelerator that you saw in the earlier slide, has now teamed up with NVIDIA to develop the co-packaged photonics. But there is also another interesting crossroad. Okay. Projections for 2030 state that the amount of AI queries that will come per year is this much. I won't even attempt naming what is this. I think it is 120 trillion. You can correct me. Right? And to manage this kind of a workload, you will need 38 Stargate class data centers, essentially thousands of racks holding hundreds and thousands of GPUs, multiple data centers and then data center clusters. And clearly this is where photonics can shine, communicating, but we also need something else. We need energy. And that energy is roughly of the order of 44 nuclear reactors supplying energy without fail safely. So this is the challenge we have at hand. On the one hand, we have AI, which has been very helpful. It has been transformative across society. And on the other hand, we also are seeing a scale up which we never envisioned. So when we are operating at scale, every little helps. So that is where we come in, we researchers, we academics, we students, and we work on these small problems, making tiny changes. And these tiny changes, simply because we are operating at scale, can give rise to very large dividends. So let's rethink.